I'm going to wait another couple of minutes because we usually get a glut of people coming in at around about bang on the hour or a couple of minutes past. Yeah, it turns out it's 4 o'clock. Okay, so welcome to the extra people. I'm going to wait another couple of minutes just in case anybody else arrives. Yeah, we've got one more already. Okay, so I'll just let in anybody who drops in by this point, but I'm going to start rambling on anyway. It's week 11, intro to statistics, one more week to go, which I'm sure you're all rather pleased about by this point. So today's hypothesis testing, we've got 7 questions on the sheet. When I looked over them, I felt like the first 5 were all fairly kind of similar. They're about hypothesis testing to try and determine whether a mean is a given value that we've been asked for. And questions 6 and 7 were about the ratios, similar to the last question that we did last week. So they were about testing whether the proportion of items or the p parameter from a binomial distribution was a given value. So I want to try and divide our attention between the two. Again, what we're going to do is we're going to take a look at question 1. I'm going to guide you through what we would need to do for question 1. You've got the advantage that I've kind of got an idea of where you might be struggling from previous classes in the week. So we'll start with question 1. We're going to use what we learn, or what we've cemented from question 1 to do the first part of question 4 together. And you'll get a chance to give that a go yourself. We will then have a look at question 4 part 2 together. And I'll just guide you through, and then we will, if the time permitting, you guys can have a go at question 6, maybe with a little bit of guidance, so that you can see how things are different in questions 6 and 7 than they are in the previous questions. I just realised I've got somebody waiting outside again. Okay, so hopefully we're all here now, and so welcome. As I said, question 1 first, and then we'll move on. Great stuff. So let me get the webcam. Let me get the thing again. Okay. So lots of hypothesis testing. So question 1, we were given some cable, We were told that the company who makes the cable thinks that it breaks on average with a load of 200 kilograms and a standard deviation. And this load has a standard deviation of 30 kilograms. We were told in the question that we're allowed to assume that the breakage strengths are normally distributed. And that the standard deviation is actually 30 kg. So that estimate for the standard deviation is correct. So the same types of things are going to affect our assumptions this week as they did last week. So whether we know exactly what the standard deviation is, whether we can assume normally distributed, all of those are going to have exactly the same impacts, because the criteria that we're using for rejecting or not rejecting hypotheses are pretty much based on the idea of confidence intervals. So we've got the same kind of factors affecting the type of formula that we use. What we were given is we were given a sample of size 40, so n is equal to 40, and we had two hypotheses initially. So we had our H0 hypothesis, which is going to be what the company thinks. So mu, the actual value, the population value, the true value that we don't know, mu, is actually equal to 200. And then my H1 hypothesis initially is going to be just that proposed mean from the company is incorrect, so not equal to 200. Now, I'm going to need a test statistic, and the test statistic in this case, I'm going to call it Z, is going to be the normalized version of the sample mean. So I'm going to take off the proposed mean, 200, and divide by the actual standard deviation divided by square root of 40. That's so that this term on the bottom here is the standard deviation of the sample standard deviation. Okay, and this is going to be a random variable because depending on the sample that we've picked, X bar is going to be different. And the number in this case that we were given for our one particular sample is 200. Oh. Jumping ahead there, 1.731. Okay, so to get this number, I need to calculate what X bar is from the information I've been given. I've been given that X bar is 8329.4 divided by 40. So what I was given in the question was the sum of all of the elements in the sample. So I need to divide by 40 to get the observed value of X bar. So for this particular sample, I've got a test statistic of 1.731. Now, the next question is, when am I going to reject my H0 hypothesis? Okay, so I'm going to reject it if the absolute value of Z, so the observed value of Z from that particular sample, is bigger than little z, 1 minus alpha divided by 2. Now, this number's from the normal distribution. So if we think about the normal distribution, it looks a bit like this. And what we've got is we've got some points here, Z, such that the area in these two ends is alpha divided by 2. Now, and then this one is centered on the actual value well, 0 because I've normalized Z. So. Now, if I observe a value of Z that's way over here, that's bigger than, if my observed value of Z is over here, then I know that there's very little chance of, well, there's a small chance of this happening if Z is normally distributed 0, 1 like I'm expecting. So I'm going to say that I think the H0 hypothesis is incorrect if, when I standardize using the assumption H0, I get a value of Z out which has a low probability of occurring. So that's essentially what I'm doing. So the key thing for the various numbers of alpha is just to look up the Z in the normal distribution table. So in the case that alpha is 5%, for example, I'm going to need to be looking at Z 0.975, which I know is 1.96. Now this is bigger than 1.731. So I can't reject H0. So the observed value of Z I found is not in the tail up here like this, it's somewhere here. So I can't say it's an extremely unlikely for me to have got that value of Z. So, you know, what the company's proposing, that the mean is 200, is not ruled out by what I've observed. And in the case that alpha is equal to 0.01, I just have to do exactly the same thing, but I get a different bound here. So what you should have found with the four cases in question 1 is that with this one here as well, we end up looking at Z 0.995, which is 2.576, which again is bigger than the 1.731. So again, can't reject. Okay. Now, things get a bit more tricky when we start looking at the one-sided case. If I'm looking at the one-sided case, so I change my H1 hypothesis. So this time my H0 hypothesis is the same. This time I'm only interested in the case when mu has been make sure I said this the right way around, when mu's been underestimated, so when the true value of mu is much bigger than 200. Now in this case, I'm not so interested in the probability that Z falls in this tail here, so I completely ignore that situation. I start looking only at the top tail. So in this case, what my criteria is going to be is I want to put all of the alpha on the top tail, so I would like the weight alpha here, and then if I observe an actual value of Z which is way over here, so it's bigger than the specified Z1 minus alpha here. If the actual value of Z I observe is much bigger over here, I want to reject it, saying that that's evidence that that H1 is true. Yeah. Okay. So I use exactly the same test statistics Z, but the region on which I want to reject is different. So in this case, rejective just Z without a modulus on it is bigger than little z 1 minus alpha. So the thresholds are going to be different from part A, because I'm going to end up looking at Z 0.95 and Z 0.99 instead. Now the values of these, if you look them up in the table, are 1.645 and 2.326. Okay. So then if we compare those with the test statistic that we've got this one here is less than the test statistic, less than 1.731. Which means that we reject the H0 hypothesis. Got somebody having a chat with me. It says, oh no, just that's fine. Okay. And then this one here is bigger than the 1.731. So in this case, don't reject H0. Now, this is the point at which I got quite a good question on Tuesday morning, because this might seem like it's the wrong way around to you. It might be like, what, I'm testing at a 5% level. Why is it that I reject H0 at a 5% level, but I don't reject it at a 1% level? Now, the thinking behind this is that if you think about where Z is going to be in each case, if I have a Z that's here, for example, like in exactly the case I've been given it's between Z 0.95 and Z 0.99. What that's telling us is that we'd expect to get that value of Z. There's only a 1% chance that we would be in this bit of the tail, but there's a 5% chance that we would be in this percent of the tail, this bit of the tail. So we're going to be rejecting more values of Z, the bigger the value of alpha. So as alpha gets smaller, so as we are looking for more accuracy, we're saying like we only want to be rejecting, accidentally rejecting a value of Z 1% of the time. So you can think about it like in the sense that it could be the case that mu genuinely does equal 200, and in 1% of the cases you're going to be rejecting that hypothesis even though mu is equal to 200 because it's that far into the tail. So that's what the thinking is there. Okay. So hopefully that's been helpful. A little quick run through when we reject and when we don't in question 1. So the first thing I want you to do is to take a look at question number 4. In this question, we've been given some batteries rather than some cable. We've got n is equal to 20. We've got the same normality assumption. We've got a proposed mu of mu0 equals 250. We've got a known standard deviation, 8.7, and we've got a known, well, we've got an observed value of X bar from one sample, which is 252.96, and you've been asked to test H0 of mu is equal to 250 and H1 mu strictly bigger than 250. So have a think about how you're going to do that using what we've just spoken about and what our rejection criteria should be. You were asked to do it at 5% confidence level. So I'm going to give you a few minutes to give that a go. Maybe not quite 5 minutes, but we'll get probably close to 5 minutes for you to give that a go or check your answer. And then we'll take a look at part 2 together, where we're looking at the probability that H0 is rejected for a given value of mu. Okay, so let's come back to talking about this. So we need to use the same test stat as before. So we're going to need to normalise the sample mean that we've observed. So we're going to use Z is sample mean minus the hypothesized mean, mu0, divided by sigma, so the actual standard deviation of the population, divided by square root of n, so that this altogether is the sample expected sample standard deviation. So this value in this case is 1.521. So as above, we're going to reject H0. So we've not got enough evidence to suggest that the company's right, and mu equals 250 if the value of Z exceeds little z 0.95, which we saw before is 1.645. All right, so we can see this is not true. This our value of Z is smaller than the threshold amount, this one. So we've not got enough evidence to reject H0 in favour of H1. Okay, so I hope you got there and you were happy with that. I've got somebody waiting outside. So I'd just like to apologise for leaving anybody who's just arrived outside. I only just noticed that you were there. I don't think you've missed too much. We've been talking about question 1 and the first part of question 4. And we've just seen that we can't reject the hypothesis H0 in the first part of question 4. So we've just not got enough evidence to say that the company's proposed lifetimes of the batteries is wrong. Okay. Now the second part of question 4 is a bit more tricky. And the first thing I want to try and help us with to try and get there is suppose that if the sample mean in question 4 is actually 250. So if the H0 hypothesis is correct, when we take a sample of size n, so a sample of size 20, and calculate the test statistic, 5% of the time, we're going to get a value that's bigger than 1.4645. So we're going to reject the hypothesis that H0's true. So we're not going to be able, we're going to reject the hypothesis because we're going to get a value that's bigger. So we're going to be in the case where we're like rejecting H0 in favour of H1, even though H1 is actually true. So if mu is actually equal to 250, it's a 5% chance of selecting a sample such that when we calculate our test statistics, that it's bigger than the threshold amount. Even though it was actually true. So that's sort of where we are in the basic situation. Now, what the question has asked us is if mu is actually 255, when are we going to get a similar kind of effort? So if mu is equal to 255, what chance is there of selecting a sample such that Z is less than this barrier, so we don't reject it, even though the hypothesis was actually false? So. So that's sort of what the question is asking us. And I think one of the things that may be confusing when you first look at something like this is you're thinking, well, but there's an X bar in there, and you know, I just know what X bar is because I've got this sample and I've calculated what X bar is. How can we be calculating a probability like this? And you've got to be thinking, well, that's just an example of what X bar is. You know, we could take lots and lots of different samples, and we want to be, you know, we've got this one particular sample that we've examined in part 1, but now we're going to be thinking more generally about how samples are going to be working. So the first thing I want to be thinking about is if our proposed value of mu is 250, we reject H0 if the test stat is bigger than 1.645. Now I can rearrange this for an expression in terms of X bar. which is going to give me X bar is bigger than 250 plus 1.645 times 8.7 divided by square root of 20, because I've got 20 elements in my sub, and this number is 253.2. So so the probability that X is rejected. So the probability that I select a sample such that H0 is rejected So this is what I want to be examining. And what I'm going to try and the first thing I'm going to do is I'm going to standardize both sides of this event here, but using what the actual mean is. And I've been told in the first instance to use 255. So I use the actual mean in there. Now I know that in the case of where I'm standardizing by the right mu rather than the potentially incorrect mu, that this thing here is a normally distributed random variable with parameters 0 and 1, because it's been scaled correctly to have parameters 0 and 1. So at that stage, I can write this probability in terms of the CDF of the normal distribution. I'm going to get 1 minus 253.2 minus 255, 8.7 divided by square root of 20, this one. And what can I do? I look it up in the table and I get a value of 0.2. So what I'm actually finding is that if the actual value of the mean is 255 rather than 2.0, so 250, then I'm actually going to get a Z out 82% of the time, such that I can't dispute the company's claim that it's actually 250. So it's quite difficult, really, for me to tell the difference between what's happening in those cases. Actually, is that the right way around? Okay, yeah. Probably to reject H0 when the conclusion. So we've got an % chance that we reject the hypothesis that equal to 250. Actually, so that's how you can see how that works. Reason why this one, actually, Just going to check that I've got this correctly labelled because I've numbers. I've got was number 7. So what I'd like you to maybe have a look at it with what we want to be doing is in the first part we want to be thinking about what our hypotheses are again. So we want to be testing H0, that the proportion of people is actually correct, that it's 0.1, and H1, the proportion of people is not equal to 10%. Now, what we've observed, we've got a big sample of 400 people, and we've observed that 47 of them are right-handed. So we've observed a proportion of 47 over 400. And we think, well, we know that people are either left-handed or they're not left-handed. So the number of left-handed people in a sample of size 400. Who are left-handed. Let's call it X, is going to be binomially distributed with parameters 400 and P, where we don't know what P is. P is what we're trying to test for. Okay. Now, thinking back to last week, the test statistic that I propose using is Z is equal to P hat minus P naught. So the proposed value of P, so 0.1 in this case. And we're going to want to standardize by the standard error of the proposed value. So okay, so I propose using this test statistic. And the first thing we want to be doing is saying, well, what are we expecting Z to be doing? I'm going to propose that we can say that Z is approximately distributed normally with parameters 0 and 1. And earlier on in the course, we saw when we can approximate the normal distribution, the binomial distribution with the normal distribution. So when can we approximate the binomial distribution with the normal distribution, and is that criteria satisfied in this case? Okay. And if it is, then hopefully you're going to be able to proceed along the lines of question 1 to test the hypothesis. With the second part, you can proceed very similarly as to question 4, part B. But we've got an extra complication that the H1 hypothesis that we're now testing is not equal to rather than greater than. Okay, so hopefully with those couple of little extra prompts, you should be able to get to a solution for number 7. So I'm going to give you the rest of the time in this class to give it a go. If you can remember when you can approximate the binomial distribution with the normal distribution, maybe test that criteria, make sure you're satisfied with it, and then decide how, you know, what kind of rejection region you're going to use on Z. If you can't remember what it is, maybe just assume that I'm right in saying that it's approximately distributed normal 0, 1, and test the hypothesis in the first part. And then if you've already got through all of that, or you've done that in advance of the class, have a think about question 2. Now, I don't think you're going to have enough time to crack on and actually do the full calculation. You'd probably need a solid 10 minutes to actually do it. But have a think about looking at the method that I've used for 4B. What's going to be different if I'm dealing with the H1 here, which is not equal to rather than bigger than? And how's that going to complicate my life a little bit? Okay. So yeah, I'm going to give you till the rest of the class, till the end of the class to crack on with that. So yeah, I'm going to just stop talking, and please feel free to direct message, talk to each other in the chat, anything like that, if you want a little bit of support with finishing off question 7. Okay, so what I'd like just to say to finish off is in part one, you should have found a value of Z, which is 1.1667, which is less than 1.96. That's the value of Z 0.975. So we can't reject H0. So we've not got enough evidence to dispute the claim that 10% of people are left-handed. What my question with part two was, which was about what becomes more complicated, was that here, when we're looking at a probability of selecting a sample such that H0 is rejected, we're going to have a two-sided probability. That's going to lead us to having a two-sided probability here and also here as well. So we're going to have to look up two separate values in the normal distribution table in order to proceed. But hopefully you at least got the first part of that. Okay. Now I'm going to hang around because I've got another identical class starting at 5. But if you're happy with the answer to that and you've not got any questions, feel free to leave. Have a lovely evening, and I'll see you all next week for the final class. It's even more hypothesis testing, so obviously it's going to be super fun. Okay, so the value of P0 was 0.1 because it's the proposed value of P under the H0 hypothesis. welcome to anybody who is just joined me for the 5 o'clock class. You're very early. Good, well done for being so early and well organized. Also, well done to anybody who has the endurance to still be here, who wants to sit through a double tutorial. All I can say is wowzers. Settle in. We're going to be doing some questions from exercise sheet 11 because it's week 11. We are going to do question 1. Well, more precisely, I'm going to do question 1 to show you what to do to start off with. Then hopefully with that level of understanding, we're going to be able, you guys are going to be able to do question 4, part 1. I'm going to show you question 4, part 2. And then hopefully with all of that information and maybe a couple of little hints and prompts, you guys should be able to do question 7. Now, there might not be time. Last hour, there was not quite enough time to give you more, the students more than 5 minutes to do question 7, but we're going to give that a go. What else do I want to say? Yeah, let's come back about 10 minutes time. We'll go from Hello, so welcome everybody for the 5 o'clock class. Just gonna leave it another minute or so for additional people to show up, because we're a little bit light on the ground compared with how many people normally come. So the plan for today is that we're going to do question 1 together, so that we can see how all of this hypothesis testing stuff works. Then you guys are going to have a go at the first part of question 4, because you should be able to do that after you've seen question 1. Then we're going to do question 4 part B together. Hopefully that'll give you some kind of idea as to why we're interested in such things and what exactly is going on. And then with any luck, we will have a bit of time left for you guys to have a go at question 7, which is different from the first 5 questions on the exercise sheet, because it's about proportions, again similar to the final question that we spoke about last week. Now you're going to see similarities all of the way through with the types of assumptions that we're using as with last week, because the rejection regions that we're studying are very, very similar to the confidence intervals that we were looking at last week. Yeah. So let's crack on. There's about 18 of us, which I think was pretty much exactly the same number as last week. So let's start. Okay, so same rules as have applied all of the rest of the semester. Say things in the chat if you like. You can say things to each other in the chat. Of course, if you do that directly, I will not have the foggiest. Or you can talk publicly to each other in the chat. You can talk to me, wave at me if I write off the bottom of the page and can't see what I'm doing, or anything like that. Point out to me if I say something wrong, or if you've got a question about what's going on. Okay. So with question 1, we were given some breakage strengths of some cable. And the company was saying that they think that the mean breakage strength is 200 kilograms. They think that the standard deviation of those strengths is 30 kilograms. And they also think that the distribution of the weights at which the cables break is normally distributed. Now, tests have been run on 40 lengths of cable. Oh, sorry, I need to let somebody else in. So we've tested 40 bits of cable, and we want to know, is the company right? Is the mean breakage strength of the cable actually equal to 200 or not? So in the first part of the question, we looked at 2 hypotheses. We looked at the H0 hypothesis, that the actual mean is 200 as the company proposed. And the H1 hypothesis was that this is just not true. It's not equal to 200. Okay. So the first thing we need is a test statistic. And the tests that we're going to use, I'm going to call it Z. It's going to be a normalized version of the sample mean. And under the H0 hypothesis, it's going to be normally distributed with parameters 0 and 1. So if H0 is true, this Z should be normally distributed with parameters 0 and 1. So if I put the numbers from the question in there, I'm going to end up with a Z of 1.731. Now, if I think about what the normal distribution looks like, it's a symmetric distribution like this, and it's tailing off at each side. So I'm going to be putting a weight of alpha divided by 2 in each tail. And then I've got my observed value of Z. Now, if this is correct, if it's from a distribution with a normal distribution with parameters 0 and 1, if I get a really, really massive value of Z out over here, this is going to give me an indication that I was wrong to be thinking that this is normal 0, 1, because there's a very small chance that the value of Z that I get is all of the way over there. My rejection region is where the modulus of Z, so where the absolute value of Z is bigger than little z 1 minus alpha divided by 2. So it's in the tail such that the two tails added together have a probability of alpha. So what this causes is for if H0 is actually true, so if that normal distribution is actually true, we will reject Z alpha % of the time. So if H0 is true. So we'll get a Z that's sufficiently big that will reject the hypothesis that mu is equal to 200, even though mu is actually equal to 200 alpha % of the time. So that's what we need to be doing. So what I've then been given is two values of alpha. So in the case that alpha is 5%, I can look up Z 0.975 in the normal distribution table. I get 1.96. Now 1.96, that's bigger than this value. In that case, this condition is false. So this is not true, so I can't reject H0. I've not got enough evidence to dispute the company's claim that mu is equal to 200. And something similar happens in the case that alpha is 1%. Here we've got 0.995, which is 2.576. Again, it's bigger than 1.731. So again, I can't reject H0. So the thing that's different in part 2 is my H1 hypothesis is now that mu is bigger than 200. So in this case, I'm not too worried about if the test statistic that I find is abnormally small. I'm only interested in if it's abnormally big. What changes is how I assess what the rejection region is in this case. So I'm going to reject H0 if the value of Z is bigger than Z minus alpha, which means that there is a alpha % chance that z exceeds little z1 minus alpha. And so there's an alpha % chance that that happens, and we reject H0 even though it's true. Okay. So in this case, the little z's that I need to look up are different. In the case that alpha equals to 5%, the little z that I'm looking up is going to be 0.95 because I'm only worried about one of the tails. Yeah, everything's gone off the bottom there and nobody said anything. Okay, which is 1.645, this one. Okay, and this is actually less than the value of z I calculated, the 1.731. So in this case, we can reject H0. Now, when we reject H0 like that, it doesn't necessarily mean that the true value of mu is 200. It just means that the chance that this value of z naturally occurred, so the probability that z was this big when H1 was true was less than 5%. So that's why we're rejecting in this case, is because there's a small probability that we'd get a z this big if H0 was true. So we're thinking z is giving us some evidence that we can't suggest. Yeah, so yeah, exactly, we can reject H0. Okay, so with that in mind, what I'd want you to look at is question 4, part 1. And you should be able to do something relatively similar. So the first thing you need to be doing is find your test statistic, Z. Find your rejection region for H0. And then draw a conclusion. So can you conclude that H0 is true is the final thing I want you to look at. So I'm going to give you guys a few minutes, maybe 3-4 minutes to give that a go. Hopefully you've got the access to the sheet so you can have a look at the parameters on the question to do that. So calculate your test statistic, write down what your rejection region is, and then draw yourself a conclusion. Okay. Okay, so if we take a look at the question, we can see that we've been allowed to assume normally distributed lifetimes again. So that's fine. And we've also been given the standard deviation for the actual population. So we can calculate our test statistic in exactly the same way as we did for question 1. So we calculate with Z bar minus the proposed mean, mu0, and divide by the expected sample standard deviation, which is sigma divided by n, the square root of n. Putting in the values that we've been given in the question, we end up with 2.96 divided by 8.7, and then all of that times by the square root of 20, because we've got 20 elements in our sample. So our test stat is 1.521. So hopefully you've got those values from the question. So with that in mind, we need to think about what the rejection region is going to look like. We've got a one-sided H0 hypothesis. We want to reject if Z is bigger than little z 0.95, because we've got a one-sided H0. So one-sided H1 hypothesis, so mu is bigger than 250. That's the H1 hypothesis. And this value, little z 0.95, we've got that from the previous question as 1.645. Okay, so what have we got? We've got the observed value of our test stat, 1.521. It's definitely smaller than 1.645, so we can't reject H0. Okay. So what's going on there? So it doesn't necessarily mean that H0 is true. It just means that the value of Z that we've observed is reasonably likely under the hypothesis H0. So we don't have enough evidence to completely chuck it out. Okay. So the next bit we want to be looking at, we'll give a go together, is the second part. And for the second part, the first thing we want to be looking at is for what values of X bar do we reject H0? Okay, so hopefully you would only need a minute or so to answer that. Have a think about it in terms of the definition of Z here and the criteria that we're going to be using to reject here. So hopefully you can see that we're going to be rejecting H0 if this condition holds, and we've got Z is defined in this way, which we can rearrange for X bar. So we're going to have X bar minus 250 divided by 8.7 divided by square root of 20 is bigger than 1.645. So this is where we're going to be rejecting H0, and that this is going to be equivalent to, we can just rearrange it to make X bar the subject. Okay. And the number I end up with here is 253.2. Just to summarize, we reject H0. The event we reject H0 is exactly the same as the event that the observed mean for a particular sample, and not necessarily the sample that we looked at in part 1, but any sample of these batteries has an X bar that's bigger than 253.2. Okay. So we want to be looking at this probability, and we want to be saying, and we want to try and evaluate this in some way. So the probability of this event, we want to try and evaluate it in some way. So what we can do is we can say, well, if I actually did know what the value of mu was, I would know that when I standardized with that correct value of mu, I would get a normally distributed random variable. So when I find the probability of X bar being bigger than 253.2, if I standardize by the actual value of the mean, then I get a random variable that's normally distributed with parameters 0, 1, 1. So the first thing I need to do is that precisely that. So the mu here is the actual mean. And I need to standardize the value of 253.2 as well. Okay. Now, because I've used what the actual value of the mean is, this random variable here should now be normally distributed with parameters 0 and 1. It was still normally distributed before, but possibly with different parameters. But now that I've standardized it correctly with what the actual mean is going to be, it's going to be distributed normal 0, 1. And then I can evaluate this using the normal distribution table. So I'm going to end up with 1 minus the CDF of the normal distribution at this value here. 253.2 minus divided by 8.7 divided by 20, this one. Okay. Now for the two values of the actual mean that I've been given, I can evaluate this. So if the value of mu genuinely is 255, I find that this value, by looking this one up in the normal distribution table, is 0.82. So what I've found is the probability that I reject the hypothesis H0 when the mean is actually 255 is about 82%. So clearly, if the actual mean is equal to 2.55, H1 is true. Because the actual value of the mean is bigger than 250. So I should be rejecting H0 in this case, but I'm only actually rejecting H0 in 82% of the cases. So in 18% of the samples that I would look at of these batteries, I wouldn't be able to reject the H0 hypothesis. I wouldn't be able to disprove that the company was wrong in saying that the mean was 250, even though the mean was actually 255. Similarly, you can do the same with the other mean. You just put the value of the mean in there and then crank out the final number, draw a similar kind of conclusion. Okay, so hopefully that's been helpful. So we've got lots and lots of time to look at question 7. Question 7. So let's all look at question 7, part 1, first of all. So what we've got is suppose, well, we've got a sample of size n is equal to 400. We're going to ask these 400 people, are you left-handed or are you right-handed? We observe that 47 of them say they're left-handed. So we propose that the proportion of them that's left, the probability that any one of them is left-handed is 47 divided by 400. Now, the actual number of left-handers people in the sample is going to be a random variable x. It depends on which sample of 400 people I'm looking at. That's going to be binomially distributed with parameters 400, because I'm asking 400 people, are you left-handed or not? And parameter p, with the p being the actual probability of being left-handed. Okay, so the actual probability of being left-handed. And p is what I want to try and determine. So I've been told in the question that there's that the proposed value of p is 10%. So the proposal is p0 is equal to 0.1. And what we want to be testing is my H1 hypothesis is going to be, well, that actual probability of being left-handed p is going to be equal to p3. And my H1 hypothesis is going to be that this is not true. So p is not equal to p0. Okay. So what's my test stat going to be? So I'm going to propose to use the following test stat. So it's going to be p hat minus p0, and then divide by the standard error of the proposed value of, n divided by n. I'm getting too used to writing those square roots, so it needs to go like that. Okay. So what I want you to take a look at doing, first of all, and I'm going to give you 5 minutes or so to do this, is calculate Z. Okay. And then my second question is going to be, can we approximate Z using the normal distribution with parameters 0 and 1? So hopefully you can remember from a point earlier on in the course a criteria that we can use to determine whether that's a decent approximation. So either look it up or have a think about, you know, what kind of criteria we could use to prove that we can definitely do that type of estimate. And then when if you can't remember how to do this one, just jump on to the next thing I'm going to ask, and then using the fact that Z's approximately distributed normal 0, 1, draw a conclusion about whether or not you can reject H0. So those are the 3 things I want you to look at. The second one is optional if you can remember how to do that. If not, just jump onto the final one and just assume that you can definitely approximate Z with normal 0, 1 and test the hypotheses we've been given here. And I'm going to give you a solid 5 minutes or so to give those 3 things a go. and then we'll come back, we'll run through it, and I'll give you a little bit of a hint as to what you can do for the final part of question 7. Oh dear, thanks for pointing that out, Majid. I guess I should go back a little bit. So I was saying we can just plug in the values. Hopefully you can plug in the values and get 1.167. With the question about whether or not I can use the approximation. Earlier on in the course, I think it was question 1 on one of the exercise sheets from before the Easter vacation, we saw that if n is nice and big, we can use this approximation, and the exact criteria is if n is bigger than 9 times the maximum between these two values. If I stick my value of P0 in, I get 81, which is definitely smaller than 400, so I'm good to use the approximation. So then I'm just in a situation which is pretty similar to the questions that I've looked at before, because I'm interested in the 5% criteria. So alpha is equal to 0.05. I'm then interested in the rejection region. So I reject H0 if the absolute value of Z is less than Z1 minus alpha divided by 2. In the case that I've got this 0.05, I know the value of this one because it's ingrained in my brain because we use it so much. It's 1.96. So then if I look at what my test stat is, it's nice and small. It's 1.166777. So this criteria, my inequality there is the wrong way around because I just got too enthusiastic. So this here is false. So we've got 1.1667 is actually smaller than 1.96, which implies can't reject. Now, that doesn't necessarily mean that H0 isn't false. It just means that the observed value of Z that I've got it isn't big enough for me to say that there's a low probability of Z0 being true. Okay, so I can't reject the H0 hypothesis, and then we're done. So hopefully you got there, hopefully you managed to do those 3 bits in the 5 minutes I gave you. I think the tricky one is justifying that you can use the normal distribution criteria, because if you started trying to use any other criteria on this test stat, you'd probably get yourself stuck pretty quickly. So that's the key thing that you want to be remembering. When can you approximate binomial distribution with a normal distribution? The answer is when you've got a nice big N. Okay, now for the second part of question 7, we were asked for something very similar to question 4, part B. We were asked to find the probability of a rejection region. Let me just look at the question again. Right, yeah. So we were told to, what's the probability we reject H0 when P is equal to 0.10. So the first thing we want to be thinking, it is very similar to question 4, part B. So if we just start looking at the event, the same as we did at the beginning of 4, part B, we should be able to get there together. Okay, so for what values of P hat do we reject H0? So we're just going to do that pretty much similarly to what we did in question 4. So, but the main difference is now we've got this modulus value. So we're going to be rejecting we're going to be rejecting p hat if this condition is true. So okay, so the first thing you're going to need to do is you're going to need to rearrange this to be in terms of p hat, so that we can you know, go from that point forward. So now what's going to be different from question 4 part B is to take away the modulus sign. What we're going to be wanting to do is we're going to be wanting to look at the first thing we're going to want to do is go for minus 1.96 is less than this value here. Which is less than 1.96. And now we're in a position where we can rearrange that event a little bit better. And then we should be able to proceed directly along the same lines as in 4 part B. Now I've run out of time, so I can't give you 5 minutes or so to give that a go, but hopefully with that little bit of a hint, you should be able to give 7 point B a solid go before the solutions to the exercise sheet are released. Although I think they're going to probably be released pretty damn quickly if they're not released already. So you might just want to refrain from looking at the solution until you've used that hint to give it a go. Okay, so thank you all very, very much for bearing with me so late into the evening on a Thursday. I will see you all next week for our final class. If you want to hang around and ask either myself or Sara-Lise any questions, feel free. If not, just see you next week, and you're very much free to leave if you wish. Okay, so I'm just going to assume that everybody who's left is either talking to Sara-Lise via direct message that I can't see, or has wandered off and doesn't need assistance. So I will see you three next week. And the same to Sara-Lise. I will see Sara-Lise on Tuesday morning.